Hello everybody, my name is Campo and I'm a postdoctoral fellow in the Kim and Duncan lab at Northwestern University. And first of all, I would like to thank the organizing committee for allowing me to present our work here at the MPS World Conference. And today I'll be talking about our new multi-organ microfluidic device called LATTICE that we are developing in the Kim lab. First of all, I would like to make some statements that everybody will agree to, mainly that current in vitro models are not capable of representing the complex tissue interactions that are found in vivo in the human body. And to correctly phenocopy endocrine, paracrine, interorgan signaling, there is a need for a microfluidic platform that's able to house different types of tissue cultures, but also to have them interact with them in a physiological manner. And to do this, you need to solve many technical and biological questions. And the first attempt with it resulted in the creation of Evotar. It's the first female reproductive tract on a chip. And this microfluidic platform, we were able to house up to 5 different tissue cultures, namely the liver, fallopian tube, ovary, uterus, and cervix. In the middle, you can see the device itself. And these tissues were able to go through an entire human menstrual cycle, 28 days long, which we could also see here in the hormone secretions. So we see this nice estradiol peak right before ovulation, and followed by an increase in hormone production by the ovary that's maintained during the luteal phase. However, there were many issues with this device, which made us go back to the drawing board and establish some different design criteria for the next iteration. And those you can see here in these slides. So first of all, we wanted it to be made out of materials compatible with hormones. I'm very happy that the previous speaker mentioned this already, but PDMS is on its way out, mainly because it absorbs hydrophilic or hydrophobic compounds such as hormones. Secondly, we wanted the device to be compatible with 24-well plate technologies. So with 24-plate well technologies, I mean the imagers you have in your lab already that fits a 24-well plate, but also the cultures that you optimized for 24-well plates with, for example, transwells or other type of cultures. Furthermore, we want it to be much more user-friendly. We want biologists to use this device, not engineers. We also want it to be more cost-effective. You can see here a first attempt of a 3D printed microfluidic device that we were doing, but sadly enough, the supposedly biocompatible resins that we used induced severe ovarian toxicity, so we had to redesign it. And we wanted to be reliable and also compatible with robotic handling, which leads us to our current iteration that we're calling LATTICE. So what is LATTICE? How does it work? It's basically made out of two parts that is placed into the incubator, namely the base station and the culture plate. The culture plate, as I said before, is the same dimensions as 24-well plates. Actually, I have one right here. It's very recognizable for normal biologists. And between the culture wells, there is a stepwise fluidic flow, which can be designed by the user itself. So whatever kind of biological question you need to answer, whatever kind of flow pattern you need, you can design it yourself. The plate is placed on the base station, and the base station has everything needed for the microfluidic flow or actuation. So it has valve, pump, and clamp motors. Furthermore, there's also some sensors for robotic integration, namely pressure and plate proximity sensors. And this base station is controlled by the computer using some very user-friendly software. So on the left you can see the user interface. You can see that we can connect up to 5 devices per computer. And on the right we have the language that we use to control the device. We call them flow scripts or culture scripts. And actually also very cool, you can see the readout from the pressure sensor. So whenever you see some higher fluctuations in the pressure. That's when the culture script is running. And so it's actually very nice for us because we can see using the software that everything's running well, so you can have confidence that your tissue, that you don't even have to touch the tissues to be sure that everything's okay. So how is this stepwise microfluidic flow? So we have a rotating valve mechanism that connects to microfluidic channels which are itself connected to the bottom of each culture well. So we have 8 culture wells in the plate and 12 acceptor and donor wells. And basically the rotating valve mechanism has a capacity to move up to 40 microliters every step from one well to the other. We also wanted to establish how precise this is. So we made what we call the pump equation, and that's basically for each command we give, how much are we moving in reality from one well to the other. So that we have done that for a command of 10, 15, 20, 25, 30, 35, and 40, and then measured how much in reality was moved. And we see this very nice linear correlation of a high dynamic range. Depending on your flow script, you can have microfluidic, but even millifluidic cultures. When I really push the system, it can move up to 3 mLs per hour, but you can go as low as 10 microliters an hour. So there's a huge dynamic range that you can have between the culture wells. Furthermore, we also established that we can do this for extended periods of times. Here in this example, we do it for 20 days. Then now that we know that the fluid flow is reliable, we wanted to demonstrate that the platform itself is biocompatible, dynamic culture improves culture conditions, and also that it's tissue agnostic. With tissue agnostic, we simply want to state that independent of what kind of culture you have, you'll be able to place it into the system. And this is basically a consequence of having it being very similar to a 24 well plate. The examples I give here are mainly reproductive tissues because we are a reproductive lab, but we culture them in various ways. So for the agarose mold, these are agarose low adhesion microwells. We use them for fallopian tube, cell aggregates, and endometrial organoids. Furthermore, you can also place hydrogel encapsulated organoids or explants. In this example, these are alginate encapsulated pancreatic islets that are just placed into the system. And then the most commonly used are the transwell cultures, where we place cultures in the transwell. We did this for ovarian explants, fallopian tube explants, and fat spheroids as well. So for these cultures, we wanted to make sure that they were thriving for long periods of time. On the top left, you can see murine oviductal epithelial cell aggregates that were cultured over 14 days. So we mainly did live stains here, and we see a high viability of the cultures over a prolonged period of time. I also included an example for the endometrial organoids. They, during culture, they assemble in a physiological manner having a cytokeratin, so the green is a cytokeratin positive signal on the outside, encapsulating stromal cells that are vimentin positive. When we culture explants, such as fallopian tube, we see that they remain viable as well, with very little cell death for 7 and 14 days. And very interestingly, so in the bottom right, this was not a fluidic experiment, but the most sensitive bioassay that our lab has at its disposal is the in vitro maturation of denuded oocytes. And so very little leachate can affect the meiotic progression of denuded oocytes. And we have published these results a couple of years ago. But mainly what we try to establish here is that using this same bioassay, we demonstrate that the culture plate performs as well as a standard 24 well plate or 4 well plate. When we move to making a comparison between dynamic and static culture. We created we created adipose spheroids, and we placed 30 of them in a dynamic and a static well, as you can see on the top left. And every 2 days, we replenished culture media for the static culture well, full media changes, and we took the spent media in the acceptor well, and we measured the glucose concentrations. So on the top right, you can see a significant difference, and it's a very nice example of what happens when you have to do static culture media changes. So every 2 days for these cultures, you have a peak of glucose and then a depletion, peak depletion, while in the dynamic well, cultures remain in a steady state situation, and the glucose concentration between the donor, so the fresh media, the culture well and acceptor remains the same. Furthermore, when in dynamic culture, tissues are in a less stressed environment, and we demonstrated this by measuring the L-lactate levels. As I showed, we are culturing many different types of tissues, and this is because we want to move towards creating a model for PCOS, and I'll give a little bit more info on this in a couple of slides. But one of the most important ones is the ovary, and here you can see a time lapse of a ovarian explant on the device itself during culture, and we can nicely see that the follicles, and actually now we're seeing ovulation for a second there. We have a nice follicular phase where FSH stimulates the follicles to grow and expand and prime the cell for ovulation. Then at day 8 we have ovulation followed by the follicular phase. And much like with the first microfluidic device we used, we were able to recreate the data with this nice estradiol peak before ovulation followed by higher production of progesterone. And as I said, we're going to use this device to create a model of PCOS. For the sake of time, I'm not going to go into too much detail, but one of the main characteristics of PCOS is hyperandrogenism, and that means there is a high level of androgen produced by the ovary. This is usually caused by LH or luteinizing hormones hypersecretion. And when we do this on platform as well, in the top right, you can see that the amount of testosterone produced by this ovary is significantly higher than the control. So we are able to we are able to introduce pathological stimuli, and they react physiologically to them. Another interesting result that we saw is when fallopian tube explant cultures are cultured in static and the microfluidic device with exogenously added testosterone. Only in the microfluidic device we see a higher expression of proliferation markers, which is also something that's been demonstrated in the past. And the fact that we only see the microfluidic is, I think, a very nice example of if you improve the culture conditions of healthy tissues, when you start introducing pathological signals, they react to it in a physiological manner. So in conclusion, LATTICE is a robust and reliable microfluidic multi-organ platform. Something I haven't said before, all of the data that I presented has been produced by 3 different labs by different operators. One of them I even trained over Zoom because of COVID. So that is a real demonstration of how user-friendly this device is. It's also made by off-the-shelf components, so the price should be drastically reduced compared to other devices. And these 2 things would decrease the barrier of entry for other labs to use devices like this. We also demonstrated the physiological relevancy that PCOS-relevant tissues such as ovary and fallopian tube can be cultured for long term, and they react to these pathological stimuli. And we think that this device could serve as an important tool for disease modeling and drug testing. And the last thing that I want to share with you all are some future perspectives. So we also made this device compatible with automatic robotic handling. So scheduling software can command our device to stop dynamic flow, lower the mechanism, take the plate out, and the plate can then be taken by a robotic arm. And in this example, we're placing it into a automatic imager that has a custom imaging profile. Oh, it's not. Oh, there you go. And in the future, we also want to include automatic liquid handlers as well. So it would really become a matter of setting up the experiment and then letting it run for X amount of time. And here you can still see the imaging profile being run. Yeah, sorry. And afterwards, it will be returned to the device and continue dynamic flow. So our future PCOS model that we envision includes islets for insulin production, liver, and fats as the main metabolic components, followed by ovary, fallopian tube, and endometrium as the main reproductive tissues. And this combined with a complex system compatible with automation would be a very powerful tool for the future. I would like to thank our collaborators, my mentors Julie Kim, Teresa Woodruff, and Francesca Duncan, our collaborators Jonah Burdett and Joe Zhao, and our funding sources. Thank you all for your attention, and if you have any questions, happy to answer.